myself, Dr. K. Durga Shyam Prasad, HOD Triply, Vignan Institute of Engineering for Women, and convener of this STC short-term course on advanced simulation tools for power electronics, electromagnetics, and power systems. I welcome you all to this program. This STC is being conducted by Triply Department of Vignan Institute of Engineering for Women, Visakhapatnam, which was established in the year of 2008 under the chairmanship of Dr. Laura Garu. It is affiliated to JNTUK, Kakinada, and approved by AICTE, India. The institution is set up exclusively for women students. It provides excellent prospect to them for attaining skills and knowledge in technology and latest trends of electrical engineering. This STC is conducted with the support of our beloved principal, Professor Jaggarajupeta Garu, my staff, and coordinators. I would like to start with the introductory note of this STC. The main aim of this STC is to enhance knowledge regarding software tools. Generally, as electrical engineers, we use MATLAB to simulate any electrical circuit, system, network, or machine. For example, in order to have treatment for any medical issues, a general physician may give only normal treatment for patients. But how a cardiologist or neurologist treat a patient in specific, same way to be more specific to acquire the output for given input with more optimistic results for the given system. The PSIM for power electronics, JMAG for electromagnetics, EMPT for power systems are used for optimistic and accurate results for given test system. So without any more delay, our resource persons will take over the session. The resource persons from PSIM Engineering Solutions Private Limited. We are conducting this STC 5 days. Day 1, introduction to power electronics, introduction to PSIM software, modeling of DC to DC converter, modeling of three-phase voltage source inverter fed induction motor drive, and maximum power point tracking using different methods, and PWM generator with A to D converters. And day 2, overview of the software and introduction to the power force software and design of three-phase DC-AC converters in power force software. From day 3 onwards, we are starting electromagnetics, and day 4 power systems. In day 4 power system, introduction to EMPT software, and day 5 modeling of wind energy conversion system using EMPT RV software and transient stability analysis. So these are the each day schedule. Each day we are conducting different modules. Day 1, our resource person G. Vinay sir, Vinay Garu, power electronics support engineer from PSIM Engineering Solutions Private Limited. He has much experience in this field. So I'd like to hand out the session to Vinay sir. And finally, I thank to Vamsi and Srinivas sir and Vishnu sir for support to conducting this STC. So, Vinay sir.
Yes. Thank you.
Sir, please hand over the session.
Yeah, sure.
So, thank you for the introduction, sir. So we will start the session. Yes, Vinay.
Okay, fine. So, good morning, everyone. My name is Vinay, as you said. Okay, now we are going to see. Okay. Before going to our today's session, I just want to introduce my company, just a little bit about my company. So yeah, first I will show little about my company. So before that, these are the today topics, which is like introduction to the PSIM software and modeling the DC to DC converter. And the same time, we do some hands-on also. We can do the buck converter design. So that I have included this. And the next one is the maximum power point tracking using the perturb and observe method. Okay. And the next one is the overview on the PW generation with the AD, means analog to digital converter in continuous mode for the TI target, means F28 335. Okay, this is the today sessions. So yeah, so our company name is PWSIM. So our parent company is called the PowerSys, which is 17 years of experience in the software selling, and we have around 8 offices around the world, and 2 of them are in India. One is Bangalore, and another one is Chennai. So yeah, and more than 40 plus employees are working in the different fields like sales, support, studies, like that. And in 2019, we have crossed 10 million USD. Okay, so this is and these are some key dates, which is like we started selling PSIM software 2002. I mean, the POWs actually started with selling PSIM software in France. Okay, and the next one is like a EMTP. We started selling 2011, and Saber 2016, and PowerForge 2018. Like this is our way. So these are the some key dates. So here you can see the PWSIM is created in 2018 by alliance of the PowerSys and ProSIM. Okay, so PWSIM is the Indian subsidiary of the PowerSys, and we offer the software, means we have our own software called the EMTP, and we have the services. Means services means in the complete range of service like support, training, and studies. These all will come in under the studies. And we have the expert community where we have the strong relation with the developers to provide the best solution. Okay, and so with our business, we have covered the all electrical domains, means which is all we are giving all the electrical solutions. I mean, where we can see here automotive, aerospace, transportation, home appliances, and electrical energy, renewable energy, electric vehicles. So these all will come. These all are the electrical solutions we are providing with the different kind of softwares. Okay. And the next one is we do PowerSys is a consulting and software company also. So where we do the engineering consulting and the software distribution both. So okay, these are the some all the softwares which are in the PWSIM portfolio. Where you can see Electromagnetics, where we can start from the Electromagnetics. The JMax software is there. So it is the comprehensive finite FEA software suite for the electromechanical and the equipment designing, like a motor, transformers, like that. And coming to the power electronics, where power electronics we have nearly 4 softwares, like a PowerForge. One is a PowerForge. It is a powerful platform to design the cutting edge and the multi-level power converters. Okay, and means we will get the cost estimation and the analysis, like losses estimation, efficiency estimation, everything we can get from this powerful software. Okay, and the next one is the smart control, where we can design the controller of the any converter. Okay, so this is for power electronics, only for power electronics. Okay, and the next one is the PSIM. As we know earlier, PSIM is a simulation software, but in the PSIM there is no limitation for the element. Means we can do the any size of simulation. Okay, and then the better perform analysis facilities is also available. And the next one is the Saber RP. So where we can do the robust design and multi-domain physical systems, advanced simulations, and all we can do, which is related to the electric vehicle, and we can do in this Saber RP. And coming to the Saber ES Designer, where we can do the optimization and the safety analysis of the electric vehicle wiring harness. Okay. And the next one is if we come to the vehicle to grid, it means where we come to the power system. So we have the software called the EMTP, okay, where we can do the complete and technically advanced simulations and analysis software for the power systems. Okay, these are the softwares that are available in our portfolio. And we have the worldwide presence where you can see our developers are from different continents, like US and Japan. So these, and we have 8 offices world. So we almost cover every continent. So we have more than 2,000 customers around the world. Means in different, like uh, here you can see Bosch is having the Sabre software, and Toshiba is having PSIM software. Like that means different, means every company is having different software, and these are some of the valuable customers that we have. And these are our contacts details. Means if we, when you are in the AMC, means when you buy the software, and when you come under AMC, if you have any queries and all, so that you can create your own query, means a ticket that anyone our engineer will respond accordingly. So okay, this is about our company. So now we will go to the PSIM software. Okay, so this is about the PSIM. The PSIM is developed the PowerSIM. Okay, PowerSIM Tech in US in 1994. Okay, and the PowerSIM is the exclusive distributor in Europe, and the PWSIM is the exclusive distributor in India. And PSIM is used more than over 70 countries worldwide by the thousands of customers like Samsung, Gandhi, LG, Caterpillar, NASA. These some examples. So okay, actually PSIM is most affordable because PSIM is like depends upon the modules, the price, everything will vary. So here you can see everything will not be like all together. It is like separated by the different modules. So we can select our own module means, according to our requirement like that. So here this is a PSIM environment, modules environment. So I will explain the modules here. So when it comes to the basic module, so which is contain the basic elements and the related functionalities like switches, MOSFET diodes, and sources and measurement things, probes, and like these all normal. Am I audible, right, Vishwanath?
Yes, you're audible.
Yeah, okay, fine, no problem. So like this, these all elements will come under the basic module. Okay, when and the remaining every are the add-on modules where it comes to the digital module. Okay, the digital module is for the system analysis in the jet domain for the DSP and microcontrollers. Means we can do the here in the digital module you will get the digital PI controller, digital integrator, digital, so all the digital which is required for the digital operation. So those elements you will get in the digital module. Okay, so digital control module. And the next one is the motor drive module. So where you can do the actually in this motor drive module you will get the all types of motors, and motors like induction motor, PMSM motor, and reluctance motor. So these are DC motors. So these all motors will come under in the motor drive module. Okay. And the next one is the thermal module, where you can do the heat loss calculation and you can create your own thermal module for your simulation. So these all possibilities are there in the thermal module. So which is very useful for the power electronics engineers. Okay. And the next one is the renewable energy module, where you can do the wind energy and solar energy, and by using the batteries and also these all you can get in the renewable energy module. Okay. And next one is the SIM coupler. For the SIM coupler is actually for interfacing the PSIM with MATLAB, where you can do the co-simulation with MATLAB and PSIM. Means like example, like if you have any control algorithm in so where you have the control algorithm in MATLAB, so that you can use for the you can use co-simulation, and that you can you can do the co-simulation with the PSIM software, which is in the power circuit in the PSIM software, control circuit in the MATLAB, that you can do the co-simulation. But for that we need the SIM coupler module. And the next one is the SIM coder, where you can get the targets, means TA targets, and also you can generate the automatic code generation. So that is also possible with the SIM coder module. Where, and these are the TA targets are like F2833, F2833, and F2803, F2806, F2802, F2837. So these are the targets are available in the PSIM. So for these targets, you can directly generate the code, and you can directly generate means by picking at the blocks, and you can create your circuit, and that you can directly generate your logic. Okay. And next one is the design suits. There are two types of design suits. Means in the design suits, there are two types are there. One is motor control design suit, and another one is a hybrid electric vehicle design suit. Where it comes to the motor control design suit, it is like a ready to use templates. It means it's just like you can give um, input to the motor control design suit, like input side means what is the DC bus voltage, what is the motor values, what is the controller values, and which so these are all inputs. When you give, you will get the output as like a accurate output. Means so you will get the fully controlled output. So that but this is like a for PMSM and induction motor, only these are available, two are available in the motor control designs. And next one is the hybrid electric vehicle design source, where you can use for the hybrid electric vehicle templates. Okay, and means just if you give the inputs, that automatically it will give the output. So this is what that's design suits. And the next one is the smart control. So as I explained earlier, smart control is like a control design and stability analysis. So these all you can do in the smart control software. Okay. And the next one is a mod coupler. So in the smart coupler, if you can do co-simulation with the model sim software, where you if you have anything like a code, FPGA code in the model sim software, that you can do the co-simulation, and you can run that code in the PSIM. Means like by the co-simulation, so you will get output in the PSIM. Okay, and so like this. And the next one is the Mac coupler. So Mac coupler and Mac coupler RT for interfacing the PSIM with the JMAG. Means the JMAG is like electromagnetic design. Like example, like one induction motor. If you have developing one induction motor in the Mac JMAG software, that JMAG that model you can work in the PSIM. Okay. Means by doing the co-simulation, and you can do like instead of the PSIM motor, you are using the JMAG motor. That is possible in this with this Mac coupler. Okay. And another one is the spice module, where you can do the spice analysis, and also where you can create your own spice model, like by using the netlist code. So like this. And the next one is PAL. So where you can do the processor in loop simulations with the hardware, means the microcontrollers. That is possible in this with this PAM module. So these are the modules are available in the PSIM software. So okay, we'll go to today content. So it's like the overview on the DC to DC converter. So okay, before going to the DC to DC converter, so I just want to classify some types of converters. Like the classification come under the different types of construction, different types of output, different types of power flow. Where it comes to the construction, there are like isolated and non-isolated. We can see that isolated means which is not separated ground to input and output. But when it comes to the non-isolated, the ground is separated by using the transformer. Okay, that is what. So that is where the construction difference in the isolated and non-isolated. But when it comes to the output, so output current, yeah, here the continuous and discontinuous, that is also depends the size of inductor, means the size of what filter. Yeah. Okay. The next one is the power flow. So the power flow also defines that unidirectional or bidirectional converters also available. Means where unidirectional is just like a normal buck converter or boost converter or separate converter. Normal converters are like unidirectional. When it comes to the bidirectional, you can wear in the electric vehicles and the battery charging applications. So there you can use the bidirectional converter. You have to use. So that's all. So here some characteristics of the DC to DC converter circuits. Here you can see the types of converters like isolated and non-isolated, and that I classified. You can see here circuit type. Okay, so in this non-isolated and isolated, the basic converters are like buck, boost. So these all will come into the basic converters. So the number of parts are means like where in the buck converter you will use like one switch, one diode, and one capacitor, one inductor. So these are the only elements. But when it comes to SEPIC converter or Zeta converters and all, you will use two inductors or two capacitors. So that's what the size, the parts will be more. So because of that, the cost, because of the less parts, so the cost also will be less, and the output power we can use for the high also. This and the ripples will be medium. Okay. And when it comes to SEPIC, it will be little more elements, right? So that's why it is little costly also. So yeah, so these are the classifications. Where it comes to the charge pump, so charge pump is like a basically for small power applications we will use like a PCB type. Okay, so where it is like a number of elements are very less, so the cost also is medium, and the output power is very small application only we use. Okay. And the next one is coming to isolated type, forward transformers converter and flyback transformer converter. So where it comes to the forward transformer converter, power converters, it is require it is like very large elements. So that's why the cost also increase in use. So you can use for the high power equipments also. So and next one is the flyback transformer, where you can medium elements. So the medium cost and the power output also you can use for the medium only, and the ripples are more. Yes. Okay. So then next one is the relationship between the switching frequency and the properties, where the properties are like a maximum efficiency, where you will get the maximum efficiency. At low switching frequency, you will get the maximum efficiency because the switching losses will be less. So that is the that is the one reason you will get the maximum efficiency at low switching frequency. But high switching frequency, you will get the maximum efficiency is less. Okay, and yeah. So the next one is the output current at the maximum efficiency. So where it comes to the low switching frequency, it will come at light loads, and the high switching frequency it will come at the heavy loads. Okay. And next one is the ripple. So where it comes to the low switching frequency, the large ripple will be there because the charging and discharging times of the capacitor or inductor will be more in this point. So that's why the maximum and minimum values will be very huge difference. So that's why that ripple will be more. But when it comes to the high switching frequency, the ripple content will be small because the charging and discharging time of the capacitor is very less. So that's why the maximum and minimum value of the inductor or capacitor will be very less. The size, so that's why the ripple content of the high frequency will be small. And the next one is the response speed. So at low frequency, the response speed is very slow, and coming to the high switching frequency, the response speed will be very fast. So these are the some non-isolated converters. You can see the buck converter, buck boost, buck SEPIC. So they are so these are non-isolated converters. So these are the isolated converters where you can see the transformer to separate the groundings. So this is what. So we'll go to the buck converter design. Okay, so where you can see here, so these are the stages to design any just like a basic buck converter. Okay, first one is like necessary parameters for the power stage. Means we need to know what is the output, what is the input, so what is the maximum current is required for the load, and these are the parameters we need to mention for our design. So that is what called the necessary parameters for the power stage. And the next one is the inductor selection, which is which is coming to the filter design. Okay, and the next one is the maximum switch current. So where it comes to the maximum switch current, because we need to know the maximum switch current to select a switch MOSFET, okay, and diode. That's what. So we need to find out the maximum current. So that is the need to find maximum current. Okay. And the next one is the rectified diode selection, because of depends upon the power rating that diode we need to select. Okay. The next one is the output capacitor selection, which is coming under filter design. Okay. So necessary parameters for the power stage. In this, so these all will come. It's like you need to mention the input voltage. What is the input voltage we have, and what is the output voltage we need to get. Okay, so this is what the main important task, where it will define which type of converter you should use, means whether you should use buck or boost. Okay, so yeah, anyhow we have doing buck, right? So output voltage will be obviously less than the input voltage. Okay, so where it and after one is the next one is maximum output current. So this we need to know to define the switch ratings and all. So we need to know what is the maximum output current. Okay, and yeah, next one is the switching frequency. One of the important factor is the switching frequency, because depends upon the switching frequency, like a ripple content will vary, and the size of the converter will vary. The size of the capacitor or inductor will reduce or increase, depends upon the switching frequency, and ripple also will vary. And so this is switching frequency is the important factor. Okay, and the next one is the filter design, based upon the input values. And current values, and switching frequency. So the filter we can design, means filter means here we can use LC filter. So yeah, so we can first of all here you can see the inductor selection, where so in inductor selection this is one important factor is called change of the inductor current. So normally there are some if you see any company inductor and all, so depends upon their rules and regulations they will provide, means like the change of the current will be like should be 10% or 20%, that you need to describe. So when you describe that, so the change of current into means multiply by the output maximum current, so that you will get that change of the inductor current. Okay, so with that only here we can calculate the inductor. So this formula actually, when you apply the KCL and KVL on the buck converter, so you will get this formula. Okay, so yeah, these are the standard formulas. Even you can see, you can refer some papers, you will get formulas, and you can try even KCL and KVL applying the so you will get. Okay, but here I just want to show what is the importance of these factors, like delta IL. Okay, and the next one is like switching frequency and input voltage. So I have said earlier, so switching frequency will show impact on the storage element size. So here the inductor size also will have the impact on the switching frequency. It is like when the switching frequency is increasing, the inductor size will reduce. That is what actually here you can see. So here, yeah, the higher inductor value, the higher is the maximum output current, because the reduced ripple current. Okay. So the next one is the maximum switch current. So here you can see the maximum duty cycle ratio. So where it comes to the duty ratio for the buck converter is like output by input. But when it comes to the hardware point of view, we need to consider the efficiency also. Okay. But in the simulation purpose, we don't need to consider the efficiency, because we are using the ideal elements maximum in the simulation. But in the PSIM, that you can give data sheet parameters, that is possibilities there that I will show. And the maximum input voltage is used because this leads to the maximum switch current. Okay, because here we need to use the maximum switch current, voltage, which we are going to get. So because of that only we will get what is the maximum possible output current. Okay, that's why. So here you can see the form, like it is coming, the maximum switch current is change of the inductor voltage. The change is like this is like a DC content, and the change is like a AC content, where you can see the charge and discharge. So so that's why we are taking the upper part. Okay, delta EL by 2 is like the upper part, and the DC current. So the maximum switch current you will get here. And the next one is the inductor ripple current. So once we because we have actually choose here the ripple content, so we don't need to use this formula again. But when we have the inductor value, means we have the fixed inductance that we need to use for any project purpose. So in that time we can go in this method. Okay, by this method we can go, because we here with the inductor value is already available. Okay, so next one is the diode selection. So here you can see the diode selection is depends. Actually, we need to select the fast recovery diodes, because the switch MOSFET is very fast. So that's why we need to use the same responding the circuits. When it comes to reduce the losses, they use the Schottky diodes, which is the fast recovery diodes. Okay, and another thing, the Schottky diodes having a much higher peak current rating than the average rate. So therefore, they know the higher peak current in the system is not a problem for your project. So next one is yeah. So this is the forward current. These are the formula like output current into 1 minus the duty ratio, and the next one is the power dissipation. So with this means the forward current value and the power value. So with this we can select the diode. Okay. So next one is the output capacitor. So here you can see the output current. So in the output capacitor, here you can see delta IL, means the volt change of the inductor also affect the capacitor, because the AC content whatever is there in the inductor output current, that change of current will flow through the capacitor, and the pure DC will go to the uh, load. Okay, that is why actually it will show the effect. Okay, and the switching frequency, as I said earlier, the switching frequency also will show effect on the this capacitor. So that's what. And the effective series resistance of the capacitor means will also add some more ripple. So we need to take care about this ESR value also. Okay. Okay. So this is the actually theory behind the buck converter. So I will at the end of the session we'll going to implement this in. Uh, okay, we'll first of all yeah. At the end of the session, means last half an hour, we can implement this in PSIM software. Okay, just then I will move to the maximum power point tracking. So yeah, here you can see this is the solar panel and this is the buck converter. Means whichever the converter you can take as the buck or boost, whatever the converter, and this is the load. This converter is depends on the your output voltage rating also, so that you need to specify and you need to clarify yourself to take which converter is suitable for your load. Okay, and then next one is the maximum power point tracking. Okay, so this actually will work normally if you take the maximum power transfer theorem. The load resistance is a load internal resistance equal to source internal resistance. The maximum power can transfer. This is the key point for the maximum power point tracking. Okay, and here this is actually here I'm going to show the perturb and observe method where we can take the input samples of the voltage and the current, so that we'll get so here you can see. So these are the samples like voltage and current. Okay, when we take the samples from the voltage and current, so we need to calculate the power. So once if we calculate the power, so we can differentiate, means with the previous power. If it is greater than the present power is greater than the previous power, then we can increase. We can differentiate with the voltage. If the previous power is present voltage is greater than the previous voltage, then we can increase the PWM value. Okay, so like this is actually this algorithm we have to implement here. So yeah, so this is what the maximum power point tracking. So yeah, and the next one is okay, I will show this maximum power point tracking once in 1 minute. Yeah, so yeah, we can use this. So this is actually because it will not work in the demo version because it is having the sub-circuit. So that's why I'm just running in my normal version. Just want to show this output, and then we'll go to the buck converter design in the PSIM demo version. Okay. So where you can see here the power output is. So this is the power output. Okay, you can see the power output, and even in here in this you can add. Yeah, I said. So this is what we have given as a input reference. Oh, sorry, this is the current output. So 1 minute. So yes. So this is the standard irradiance I have provided here. So according to the standard irradiance, our the output power also is varying. Okay. So this is what the implementation. So even here you can see this is the algorithm is used for the MPPT for a perturb and observe method. Okay. So okay, the next one is so this is actually PWM generation with analog to digital converter in the continuous mode for the TA target. Okay, so where you can generate the PWM pulses using the ADC. Here you can see the ADC, and this is the PI target and PWM module, so that you will get the output. So you will get the output as a PWM. And here you can see this is actually a normal conventional method, so that you can see. But when it comes to the implementation, the TI target, so that you need to use in this method like analog to digital converter, because any microcontroller or microchip will not take the accept the analog values, so that we need to give and change into the digital values. So that's what. So this I will show. Yeah. So okay. So these are the all examples are available in the PSIM software, and you can see coding yeah, hardware. So yeah, so this is the example I'm going to show you. So here you can see 1 minute. I can make it maximize to clear visible you. So yeah, here you can see. So this is the ADC module. So we need to so specify the ADC values. So okay, and the next one is like this is actually configuration board where you can configure the all the pins which is the required pins by you. So here you can see the digital output and serial port value. So these are the pins I have configured, and after that you can lock once. So once if you lock, it will register that configuration. So then after here you can see this is what the sawtooth waveform I have given, and here you can see this is the conventional method, 10K SIM frequency. Sorry, yeah, switching frequency. So I can run this. So when you run this, so this is actually normally output, normal TI target output. So where you can see this is the you will get output in this way, and we can even see this. This is the conventional method output. So where you can use this normal switching frequency, the same output you will get same. But if you want, when you are doing the digital domain, we need to use this ADC, and so you will get directly. After that, you can get you can generate the code also. So automatic code generation is possible here. So where you can see the code with the header files, everything you will get. So here you can see the date and time. So once if you zoom first, and so after that you can close and you can open the code to generate folder, and here you can see. So these are the files you will get from the code generation, automatic code generation. So this you can use for the TI targets implementation. Directly you can use in the code composition studio, and you can debug this code. You can use. Okay. So the next, yeah. So the next one, we'll go to the hardware design. PSIM schematic design. Okay. So here you can see. So this is a buck converter I have designed for the input is a 24 volt and output is a 12 volt. Okay. So yeah. So these are the values that you can implement and see in your under switching frequencies 20K. 20 kilohertz, and duty ratio is 0.5. So everyone can try, everyone can open your PSIM software. So this is the G of the software, okay, normally. And here you can see new, you can create the new document, okay. And if normally you will get elements, so here we can see. Yeah, everyone can open the software and start designing. You can see here the screen. So this is the actually GR the software where you comes to the elements. So this is the elements like a power elements. So where you will get the RLC branches, switches like MOSFET diodes and transformers, and magnetic elements, and op amps, other elements like so these are the basics. Okay, the next one is like a modules, the different modules. So yeah, okay, but because the demo version we can't access the modules. Okay, but you can access but we here we can access the which is all the elements for the buck converter. Okay, first you can go for the sources where you can get the voltage source, DC voltage source. You can place here, just click on there, and wherever you want you can place. And if you want to rotate this element also, you can use the right function key. Okay, sorry, right key on your mouse, so that it will rotate. Okay. If you want to leave this cursor, so then you can press exit button. Okay. So then, yeah. So the next one is like so we have used this, and the next one is like we need to keep the MOSFET. We can get MOSFET directly from here itself, and if we want to go from the elements also, we can get from the here in the switches. You will get the MOSFET. Okay. So the MOSFET you can get, and the MOSFET you need to rotate. Okay. So for that you need to use right key in your mouse. So this way you need to keep the MOSFET. Okay. Everyone, if you have any doubt, you can see this. So this is the schematic. So where you have to create under diode and inductor and capacitor also. So yeah. So you can get a diode from here. You see, you maximum elements which is required. All the elements are available here. Okay. So you can take from here, or else you can go for the library and also pick. Okay. So if you are for moving, so rotating this, You can use the right key and keep. And the next one is the inductor we need. So where you can get inductor here. And the next one is the capacitor. Hope everyone is doing right, just right. And the next one is like a load. Load we are taking as a resistance. Okay. I think you can use these all elements. Means when the demo version. So try to reopen the software once. Close software once again and open and try. And where here you can see this is the wire option. Okay, to connect one element to another element. So this wire option we have to use. So just click on the wire option and whichever the element you want to connect. So that you can click on there so that you will get. So here you can see there will be some red color. So which red color is defines the power. Okay, that is the power circuit path. It means when you are using the control type and all, it will come in the green. Okay, the next one, please connect everyone. Yeah, you can just which are the elements, just you take this capacitor example. So you can use your mouse. Okay, in your mouse that the right key you can use for the rotate. Okay, and for just leaving this option, you can just use the exit button. Okay, fine, no problem. You can do. So okay, everyone start doing. So okay, see here in the screen, you can see here the wire option where I'm placing the cursor. So you will get the wire option here. Below the Windows, here the Windows option is there, right? Okay, fine. So below the Windows option, you can find the wire key.
Vinay, could you please start with one by one from the DC source and then MOSFET?
Yeah, I will start again. Okay. So yeah.
If someone not follow, so they can start now following and they can use it.
Yeah.
So just delete everything, control and delete, and
sure.
everything.
Okay, fine. So yeah. So I'm just starting from first again. So here in the DC
so hope
source.
everyone knows about the buck converter. If no one knows about the buck converter, don't worry, you'll get able to get it in the third year, 3 or 4 months syllabus, so you can able to understand that. So, but for basic understanding of the tool, we took the basic example. It's called buck converter, where the voltage level we are going to decrease from high level voltage to lower level voltage, and this is the basic structure. So it will be very useful for you. So how to design a buck converter. So just follow these steps. It will be very easy. So how we are placing, how we are drawing the circuit, the same way you are going to replica the same in the PSIM software also.
Yes. So here itself you can get the DC voltage source. So you can just click on there, and wherever you want, just you can keep. Okay. After that, you just press the exit button to go from your cursor. So you go.
So it is called escape. I mean, in the system, in your laptop or in your monitor, desktop, you can just press escape button. So once you press the escape button, it will whatever the element you took, it will be go off. So I think most of the people are gone through multi-sim software. So it's the same kind of thing. Once you press the element, so you have to press the escape button. So it will be the element will be go off.
And
So if you want to rotate the element, so in that case, just select the element and by pressing the right key of the right click on the mouse, the element will be rotated. If not, once you place the element, don't worry, you just select the element and in the top of the window you'll have the rotate option. So we'll show you that also.
Here you can see.
So just select the element and you can click on the rotate option.
Yes.
Someone is not placing properly. So don't worry about that. So it is very easy.
Okay. The next one is the diode, where you can select here from the diode. Yeah, the diode. So for you can place here, and you can use the rotate button. Okay, this is more easy. Everyone can understand. So you can rotate. Okay, fine. So the next one is the inductor, where you can select from inductor here itself. So here, if you keep the cursor itself, it will give the name. So once if you click on there, so you can take inductor, and even capacitor also beside it in the inductor only. So you can use the capacitor also. Then after that, just take the load as a resistance. Okay, resistor here. After that, press exit. So everyone can see here the wire option is available. So to connect one element to another element, so this wire option is needed. So just click on the wire option and connect whichever elements you want. So here you can connect DC source with the MOSFET, and DC source with MOSFET to the inductor, and diode to the this junction, and the next one is inductor and capacitor. So this is the basic structure of the DC to DC buck converter. Okay. So you can connect all the elements. So once if you connect, I think hope everyone connected, right? So you can go another step. So yeah.
So if we so 1 minute, Vivek. So if someone is not able to connect, so here you can see the round dotted line. So if two wires are connected properly, it will show you the black dotted. So if it's not connected, it will be shown as open one. So Vivek, could you please show that one also?
Yes, here you can see. So this is actually the dotted ones are like connected ones from one point to another point. So that you can see. So yeah. So the
Just remove that circuit and connect only half of the way. So that they will understand the other part if someone is not connected.
Okay. So if it is like this, it will come like this. So it will not give any black dot. Okay. Once if you connect full only, it will give the black dot, and it is just like a full couple. Okay. Yeah.
Because the entire PSIM algorithm is based upon your KCL and KVL. So hope you understand. You all know about the KCL and KVL. So this is how it works.
So the next one is we can assign the values and okay.
Place the ground.
Huh?
Place a ground.
Yeah, sure. So here we can place the ground. So now everyone can assign the values. Okay, here so everyone can take it as a 24 volt. So we can keep it as a VDC. I can display this so everyone can understand easily. Okay. Yeah.
Once you double click on the properties, so the property window of the particular element will be opened. So in that you'll have a different parameters which you have to enter. So after entering the parameters, we have a display option. So in the right hand side, you can able to see. So you can check that display option. So once you check on that, the element, whatever the display name is there, so it will going to show in your particular screen.
So okay, here the PSIM another advantage is like level 1 and level 2 elements also available. but we so the level 3 is like a data sheet parameters. But now we are going to use only the level 1. So the inductor value is like 0.000125. Yeah. So this is the value you can assign here. And another important factor we can know here is like a, current flag and the voltage flag. So we don't need to keep any voltage probe across this or current probe to see the current. Okay, just if you initialize this flag as a 1, then automatically while after the simulation you will get you can see the out voltage and current across a capacitor. Okay, so here you can see. So inductor value you can place here, and next one is the capacitor. So hope everyone is following, right? So this is the capacitor value. We can change it as C. For this capacitor also same. We have the level 1 and level 2. So data sheet parameters and normal parameters. This is the ideal values which are we giving now. So we can see here. It's like so this is the values for this design. According to this design, I have assigned these values. Please keep everyone these values. Then after that, a load how much I have taken that 10. So load initially normally it will be 10 only, so you don't need to change any value. If it's not the 10, you can keep the 10 ohms as a resistance value. Okay. So we have completed the power circuit. Okay, but we need the we need switching to start the power circuit. So we need the switching circuit also here. So here there are two options. One is like we have by using the sawtooth waveform. Also you can create. You can see here by using here the triangular waveform also you can create. And another one is even this by using this gating block also we can create the switching. Okay, so we'll go with the traditional one. Just we'll see,
so when I go with the gating block now, maybe.
Okay, gating block. Okay, fine. So this is the gating block where you can see you can give the switching frequency. Switching frequency you can give as the 200 sorry 20 kilo. And this is what?
You can give the default.
Yeah. Yes. So this is like a 50 degrees double. This is like a 50 degrees. Okay, sorry, 0.5 duty ratio. Okay, because it's like a 300 degrees, right? So where you can see the switching points like a 300, 0 to 360 degrees. So we are giving it the 180, 0 to 180. So it means that 0.5 duty ratio. Okay.
So show them getting blocks.
Yeah. So this is the gating block where you can get from the down itself. Okay, in the library. Hope everyone got this gating block. If you didn't get this gating block here, so even you can use this library. Okay, in the view section you can find the library browser. Okay, if you once you create that initialize that, then you can use that. You can type itself gating block, so you will get it. Okay. Okay, that's so in these two ways you can get a gating block, no problem. Okay. Okay, next you can connect this wire. Then after you can keep the voltage probe for seeing the gate pulses. Okay. So yeah, so almost we have given every element. So final thing we need to here.
No, so we have two types of voltage probes. One is
Okay. Yeah. So we have two types of voltage probes. One is like this is like a nodal point voltage source. Means at that particular point you can see this voltage, and this is another one where you can see differential probe. So where you can see different difference voltage between the 2 points. Okay. So these are the two voltage probes are available and one current probe. And here you can see these are the voltage sensor and current sensor. So this is what the closed loop operation. You need to take the voltage signals right to simulate it. So that's why in that time you can use the voltage sensor and current sensor. Here you can see the PA controller. Also you will get here. So all the parameters we have assigned. So the next one is we need to go for the simulate. Okay. Here if you go simulate, you can see
run simulation.
yeah.
When you run the simulation and show them the difference between the simulation control and other.
Okay.
So,
Now you
so
can
go to simulate and run simulation. Go to
yeah. So 1 minute. So here you can see everyone can see PSIM. Okay, run PSIM simulation. You can directly click on the PSIM simulation. So here the simulation is was running, and 1 minute. Yeah, and I forgot to tell you right. So here you can keep this current flag and voltage flag 1 to see the voltage and current across the output. Okay, and across the capacitor also you can initialize the voltage probe, voltage flag 1, sorry, current flag 1, because the voltage whatever is across the capacitor is same as the voltage resistant voltage. So we don't need to see again the voltage across the capacitor. Just initialize the current flag only in the capacitor. Then after you can so okay, this is fine. So now you can go for the simulation run. So here you can see. So this is the old output current, output voltage. Okay. So this is what output voltage and output current you got. Okay. So here you can see this is a 12 volt we need to get. So that is what that's why we got the 12 volts as the output. Okay, fine. And even you can see 12 volt divided by the 10 ohms resistance, 1.2 amperes. So that's what you got here. The current also. Okay. And yeah, here you can see you can add another window to the screen. Once if you click on there, so the window will open, so you can see V1 is the gating block, means output will get voltage signals. Okay, so there you can see. So here you can see this is actually we have applied 0.5 degrees. Okay, but we are not getting the graph exactly what we have applied. This is reason because that step time. Okay, once if you come to the simulation simulate option, you can find here the simulation control. Okay, you click on the simulation control and just you can get one clock type symbol. Just keep one place, so this window will open. Okay, so this is like your total time, means how much time you want to run the simulation. That is what the total time. So example, if I keep this 0.3 seconds. Okay, and this step time will give the exact resolution, means clarity. Example, we can say in the normal words as the clarity. Okay, So that's what the step time also important. We can keep it at 0.6 micro, 1 micro. So now if we can run, so because of the demo version, it is having the limitation for the 600 data points, and so here you can see 0.6 only, but we have run. But waveform, the clarity was before, comparing with before, it will give nice one. Unable to correct it. So here you can see this is the output voltage getting feeds like compared with previous one. This will give like more accurate.
Vinay, can you show the zoom option once for them?
For this circuit,
Zooming option.
yeah. Here itself you see for the circuit zooming and
Results.
Oh, results. Okay, fine.
Results.
So yeah. So here you can see this is actually normal. You can zoom overall screen wise. So this is like a screen zoom and the screen zoom out. And this zoom is like wherever the point, if you want to see, just you wherever the point, just you can stretch and see. You can stretch and see what is the value will be there like that. You can see full. This is like a for stretching and.
Yeah, fine. So now just show them the simulation time also.
Yeah. So here, see, after the simulation complete, everyone normally SimView window will open. If not, you can go for that run SimView window. Okay. So in this SimView window, yeah. So this will come like this. You can go okay. So here you can add the waveforms. Okay. So these are all the waveforms we got from the simulation. So example is this is like a resistor current, so that you can add. So this is the resistor current. So if you want to add another more window, means another more resistance also, you can add one screen, and you can add a voltage across the inductor like this. Okay. And I have said right, in the capacitor will drag only the AC current, so that you can verify here if you want. So here you can see AC current. This is Vishwanath, what you say?
If someone is facing some errors, maybe check the correction once and go to the simulation control. So how to change the simulation time? So just explain the simulation time.
Okay. So this is what's the simulation control. If you click on that, double click, so you will get the time step. Okay, the time step is like how much minimum step it should take to sample. Okay, that's why. So it depends on this. Actually, the waveform that smoothness will vary, and this is like a total time. Okay, the total time defines the how much time it should run the simulation. Okay, so these 2 points should be everyone. Okay. So I have taken here is like 30 milliseconds as the time, and time step is like 1 microsecond. Okay. You can close. Just no need to save anything. Just if you close, or it will save automatically. Okay. Yeah,
this is not open source software. This is a licensed software. So if you are interested, please let us know. We can able to work on it.
So yeah, after complete everything, here you can open the PSIM simulation. You can run the simulation. Once you run the simulation, normally you see here you can see. Once if you run the simulation, this window, SimView window will open. Okay. But if not, if SimView window not open, in that case you can go for the SimView window. Here you can see SimView window. Okay. So once if you click on the SimView window, you will get this. So you can add these are whatever the parameters you want to add. So these are all the parameters we can see. So if you want to see particular voltage, like you want to see the diode across the diode voltage, you can keep a voltage probe here. Okay, the nodal voltage probe you can keep. SIM controller. Which one is that?
I have answered. I have answered.
So you can directly
The simulation control.
Okay. So simulation control everyone can get here. Okay, simulate option is there. You can see screen the simulate option. So in that simulate option, if you click, you will get the simulation control. Okay. So in that you have to click. If you click that, you will get one type of clock symbol, so that you can place somewhere.
Can I ask you a question, sir?
Yes, yes.
Yes, you can.
What is that dot above the inductor, capacitor, resistor?
This is actually input. It will define the input. Okay. So this is the input side of the inductor. So this is the input side of the capacitor. This is the input side of the resistor. If you connect in the reversal, so that polarity will change.
Okay, polarity will be not much affected, no?
Yes, yes, but it can be affected in some cases, right? That's why actually that is there. So if it is not problem,
Okay,
then you can use, yeah.
Okay.
One doubt, sir.
Yes.
Sir, how we get the clock, sir? Here?
Yeah, here can you see my screen?
Yes, sir.
Okay, here in the simulate option you can see, right? I have placed my
Yes, sir.
cursor. Yeah, in there if you click, you will get the simulation control. Okay, first
Oh,
option.
okay, sir.
In the first option,
Okay, sir.
just click on the first option, then you will get this option, simulation control.
Clock. Oh, okay,
Yeah.
sir.
Okay.
Okay, thank you.
Okay, fine. Welcome. Yeah.
Hello, sir.
Yes, yes. Tell me.
Can we give any names for voltage and current
Yeah.
symbol?
You can give any old. Actually, see.
Because
Because okay, here it is not possible actually, because once if you give the resistor name, example is like can you see my screen, right?
yes, sir.
Okay, see, if you give the resistor example like
If or not.
load, okay,
Output.
yeah, load, okay, if you give the load, so this will vary like this. Once if you simulate, okay, so you can get output is like a I load and V load. Okay.
Otherwise, you can do one thing. Instead of taking the those options, you can directly place the voltage probe, and in the voltage probe, you can give the name. So
Yeah, that is also option. Here you can see the
otherwise,
voltage.
just click on the gating. So when I just show them the gating block, gating signal, just click on gating instead of A1. The probe.
Okay.
The probe.
Okay, sir. Thank you.
Okay. Welcome.
Probe. Gating probe.
Gating probe.
Just instead of A1, just gating pulses. Otherwise, it will lose.
We get.
B pulses. You can write pulses. Right?
Okay. Okay.
Just display it. On the simulation, it shows.
Okay. Yeah, like
On the
this.
simulation, and the probe, you can able to see the pulses. Instead of V1, you will get the pulses out.
Yes. Yes.
Sir, another one.
Yes. Yes.
Another question I want to ask you.
Yeah. Tell me.
Sir, here we are using MOSFET.
Okay.
So we can go switching frequency up to 1 megahertz.
Yes.
Yeah.
So
You
instead of
can.
that, you can use the.
So why is limited to take? Is it
Actually,
taken limitedly or
no.
to reduce the ripple or up to?
No, actually, everyone is having their own device. Sorry, design, right? So I have designed this for the 20 kilojoules. You can design for the 1 megahertz also. Okay. So only thing is the filter values will change. That is what here nothing problem with this frequency, but this will affect further on the ripple and all. Okay.
Yes, sir. That's why I also said able to reduce if not you take it.
Yeah,
You
you
fix
can.
it 20 years.
Yeah, you if you want, you can take 1 megahertz also. But according to the design, overall design will change. That's it. No other problem.
Uh,
Okay.
Sir, actually, in my MTech, I did in this system only. I worked on this system
Okay.
in multi-level converter like that. But
Okay.
in that, uh, in that what I want. In that I taken 10 kilohertz only, but it is worked
See,
properly.
angular multi-level systems means that is IGBT, right?
Sir,
IGBT, you can't go for the maximum high switching frequency, okay? Because IGBT is having the high current capability, current handling capability, but it is having limiting the high frequency, okay? The switching frequency will not, you can't take more switching frequency for the IGBTs. Only MOSFET is having the more switching frequency. That is the reason you can't take more than, actually normally if you take the IGBTs like a 5,000 kilohertz, maximum 10,000 they will take normally in the practical cases. You can't take more than that.
sir.
But if
Okay, sir.
you,
Thank
okay, fine. Fine.
Hello, sir.
Yes, tell me.
So we are using MATLAB.
Okay,
So can you differentiate between these MATLAB and PSIM?
okay,
So what are the features are there compared to MATLAB?
okay. Yeah, I can say here the one major advantage in the PSIM software. Here you can see example. I can open this resistor itself. Okay, here you can see the level one. Okay, level one means the normal. This is the ideal values, right? So where you can see in the MATLAB the ideal values on. But if you go to the level two, so there you can enter the parameters for the data sheet so that you will get the accurate output values. Comparing with the hardware, you will get accurate. Okay, there will not be much difference between the simulation values and the hardware values. That is one advantage. And even in the MOSFET, if you take, so here you can do level one and level two. Level one is like some little more parameters are available, and comparing when you come to the level two, so there you can have the data sheet parameters. All the data sheet parameters you can see here. Okay, so there you can enter the data sheet parameters. So it will be more uh, good output comparing with MATLAB. That is what. Okay.
And in that spice, you can show them the spice
Yeah.
also.
Yes. And the next one is the spice model also available here. So where you can do the spice level analysis, and even you can create your own spice model also. Okay. Sorry. Because of the demo version. Okay. Yeah. So these all features will come in the normal license, not like a demo version. You can't use this spice level and all. That's what. And even you can create your own IGBT, MOSFET, and in this. So that is what the advantage. And even if you want to work with the TA hardware, so the TA targets, you will get the output code is the accurate output code is possible. So it will generate automatic code generation. I have showed earlier, right? So the same thing. Hello.
Okay, sir. Thank you.
Yeah.
And compared, one major advantage was instead of all this, speed. So
Yeah.
compared to MATLAB or any other software, it will give the most fastest simulation.
So that is another advantage. Okay. In properties, I'm getting V1. Okay, because you are getting V1 because I think you have kept only one probe. You didn't keep any other. Means you can use the current flag one. Okay, current flag and voltage flag as a one. Okay. So once if you keep the current flag and voltage flag as a one, then it is fine. Or else you can do another thing. You can keep the voltage probe here. Then you can run and simulate, and you can see the this voltage probe. Okay. See, the flag, actually, the importance of the flag is nothing like if you want to see the output without keeping any probe, then you have to initialize the flag as a 1. If you don't want to see the output, then you don't need to keep it as a 1. Okay. So if you are not keeping these flags as one, then you can use ammeter and voltmeter to see the voltage and current. That is what. That is an added advantage in the PSIM software. Hope everyone got right. So I can give one example for you people to do. You can try even maybe in the home or something. So yeah, I can give boost converter as an example. So yeah. So this is the boost converter. Yeah.
So someone asked whether PSIM is used for dynamic analysis. So yes, it will be useful for auto code generation directly for text assessment targets. So automatically code will be generated and you can use the code in the Code Composer Studio. So it will be useful for dynamic analysis. Is it possible? So Dr. Srinivasarao. So if possible, we can show you one example how it works. Earlier we have shown you for the dynamic analysis, so how the code is generated. So all this part will be used for auto code generation for text instrument is possible. So TI is supporting, PSIM is supporting right now TI codes, so all TI microcontrollers. So all the FA02, FA03, FA07. So all these microcontrollers are directly work with PSIM. So apart from that, you can do the processor in loop simulation. So where your system will act as a processor and directly can vary the parameters from the system itself. Then you can control your motor or anything. So processor in loop also is possible. Even in the hardware in loop simulation, Typhoon HIL, so very big company, Typhoon HIL, they are using PSIM as for their power circuit generation. So the power circuit will be in PSIM. They will design the power circuit in the PSIM, and the control circuit they will use in the controller part, and they will use in the Typhoon HIL. So, so we have a lot more experience in all those things. Closed loop of converter. Yes, we'll show you the code closed loop of the converter. Vinay, could you show them the one basic analysis of closed loop, current mode control or voltage?
Okay.
Control
Okay, fine.
So I just take one example directly. So this is the average current mode control where we are taking the PI loop. So tomorrow we're going to show you the smart control, which is one added advantage. So we'll show you that part also in the tomorrow session.
This is the current control actually. Yeah.
So just explain that overview kind of. So we took the current sensor from the power block and we are connected to the PA block by taking
actually we have taken the current current as a signal. So here you can see that this is the current sensor. So we took the current sensor output, and that current sensor output we are comparing with the reference. So reference is like 2.4 amperes. So that reference, and so by we will get when we are differentiating this, so we will get the output as a negative feedback. So that is error we are giving to the PI controller. Okay, when we give the PI controller, so PI controller tune and it will give the reference signal for the gating. So that we are comparing with this. Okay, so then you will get the output pulses where I can show you here. I can run simulation and show you. Yeah. So this is the output voltage. So this is the output voltage we got, and next one here we can see the carrier voltage, and this is the VM is the voltage we got from the PA controller. So yeah. So here you can see this is what. So it will generate the output pulses. Okay. So here you can see.
Yes, Vinay, you can give them this task. You have given the task or not?
Yes. Well done.
So we are going to your task. Now we have designed the buck converter. So the same way you can able to design the boost converter also with that parameters which you are giving.
Yeah. So everyone can see here. This is actually converter for the 12 volt to 24 volt. And everybody can 1 minute, Vishwanath, one second. Yes.
So you can,
So everyone see here the input is the 12 volts and output is the 24 volt. So this is the boost converter you can find, right? So the resistance is the 10 volt and your frequency. So here you can see the switching frequency is the 20 kilohertz. Okay, so that you can give. And the next one, if you are trying that design normally from the any textbooks or something like, if you are trying to design, then you can do one thing. So the change of the inductor current, you can take it as a 20%. Everybody can note if you, or you can take directly these values.
so as we are explaining the basic of the PSIM, we are not taking any op amps right now. But if you want, you can able to work in order to generate the PWM pulses. You can able to take the amplifier circuits or anything. So that you can able to design. So most of the people are new to the PSIM software. We are taking only the basic circuits, basic design.
So and so here you can see the change of the current, you can take it as a 20%. Okay. And the change of the voltage, you can take it as a 5%. So if you want to calculate everything, or else you can directly try these values. Okay, L value, C value. So if I think better to take a photo and build the circuit.
So otherwise, you can take the same buck converter, just replace the MOSFETs, IGB, MOSFETs, and the diode.
Yeah, in the boost topology.
Only just change the values of DC voltage, 12 volts, and make it into and the output as 24 volts. So fuzzy control is not possible in this part, but if you want, you can able to interface with the MATLAB and you can able to design that. So here mostly we are in the PSIM software, we are mostly concentrating on the power electronics designing, so the power circuit and the control circuit. So the fuzzy logic, it's basically if we have this as a mathematical modeling, that can be possible, but mostly it will be a written type program. So instead of that, you can able to use the mathematical functions.
So yeah, hope everyone note this converter, right? Boost converter.
So yes, so thanks everyone. So we'll just try this particular boost converter by tomorrow. If any doubts is there, we can able to explain by tomorrow.
Yes.
Off. So and then we'll show you the two other softwares. One is Smart Control, one is Power Forge. And after that, we'll design some other example by connecting the motors, and we'll see the results. So
here you can see this is what the tomorrow
session.
So here you can see the overview on the smart control software, overview on the power software. And the next one is we can try hands-on like a VSF induction motor tomorrow. Okay, and I can give the overview modeling of the 3 VSF induction motor. Okay, with the field orient. This is overview, and this we can try VSF. We can try on the hands-on tomorrow. Okay.
Sir, can you just please show us the buck converter, sir?
Buck converter.
So can you just show us the please? Thank you. Okay.
Yes.
Thank you, sir. Thank you.
Okay, fine. Okay.
So kindly fill up the forms we have shared in the chat window. So if you have any queries is there, you can discuss with Shyam sir.
Yes.
So if someone is getting an error, please reinstall the demo version properly. So if someone is not able to get taskbar view is not activated to view the results. Exactly that.
Dear participants, do you have any doubts? Please ask to Vinay sir.
Hello, sir.
Yes.
the purpose of that time block, sir? Is it necessary for every simulation?
Yeah.
See,
That is actually.
basically, in the MATLAB, what you'll do is you'll run the simulation with a specific time. So in PSIM, if you want to run for longer times, you have to use the simulation control. So this is the mandate. By default, PSIM simulation will be 10 milliseconds. But if you want to run for a longer time, for 0.1 seconds or 0.05 seconds, you have to use the simulation.
Also to check time. Okay, that is also like a normally it will be like a 10 to the power of 5. But if you want to change any micro and all, then you need to use.
Okay, sir.
Fine.
Thank you, sir.
Thank you.
Hello, sir.
Yes, sir.
Hello, sir.
Yeah, tell me, sir.
Sir, regarding you have used comparator where you have used diode also. What is the purpose of using diode, sir?
Where?
No, it's not a diode. It's
No. In conventional way of triggering the switch MOSFET.
Okay.
You have used comparator. You use the comparator and cascaded with the diode.
This
what
is
is the purpose
actually,
of using the diode?
yeah, this is not diode actually. This is a on and off control actually. This is a block for triggering getting signals to power. This is actually this control level, right? So to giving the control level to power level. So this on and off switch we should use. Okay. This is not
What
diode.
is the name of the block, sir? What is the name of the block?
On and off controller.
Controller.
Yeah,
Okay,
here
okay.
itself you can see. Wait,
Can you show me?
Here
Can you show me how it?
Yeah. Can you see my screen?
Okay.
Yeah, here itself you can see. This is what you can use that directly.
Basically, it's a triggering block, sir. So one time it will be on and one time it will go off. So it will give the 0 ones.
Okay, then based upon the input getting from that block, then that is going to be action will be taken. Right?
Correct.
Okay. Thank you.
Yeah, sure.
So thanks everyone. So we will catch up tomorrow sharp 10 a.m. So please do the necessary exercises which I have sent to you. And if any queries is there, you can write us a mail to either to Vinay or to us, or we can send it this one also. So in the chat window you can able to see. So you can able to send to g.vinay@pwsim.com or n.vishal@pwsim.com.
Thank you, Vinay sir. Thank you, Vishnu sir.
Thank you,
sir. Please continue within 5 minutes, sir. I will share the link in chat box.
Sure.
Yeah, sure.
Thank you.
Okay.
So one of the participants is sir, Vishnu sir.
Sir, tell me, sir.
Yes, thank you.
Sir, one participant is asking, what is the price of licensed version, sir?
So you can write us a mail, so we will share with them. So pricing part, I think we can write to sales@pwsim.com. So our sales manager will help you able to help out. So if someone wants to purchase, I can write a mail to sales@pwsim.com.
Okay, sir.
Okay.
Thank you.
Okay then.
So we are keeping for a couple of minutes, so everyone can download the feedback form. By 11:35, we'll close the session. When you can stop the recording, please.
Okay, fine.